In an earlier video, we talked a little bit about how different objects naturally vibrate at particular frequencies called their natural frequency. This leads us into understanding how different musical instruments can be adjusted to create different notes or different tones. To understand this, we first need to look at how waves react when they hit different boundaries. So if the boundary is loose and it's not a fixed boundary, then what happens is that the incident wave comes back on the same side of the spring or in the medium. But if we have a fixed boundary, then the wave will invert as it comes back, flipping over. And this allows for the waves to constructively and destructively interfere with each other depending on how they meet up. Let's take a look at this situation here. This now switches to a continuous wave. And this is what happens in most situations. Waves are created, and as the wave inverts, as it reflects, it sort of somewhat combines with the incident wave, but nothing particularly special comes out of it. It seems kind of random. Let's take a closer look at why that is. If we overlap two different waves and we look to see how they combine or superpose on top of each other, we can take a look at some specific points and try to understand why the wave has a particular look to it. So for instance, at part A, we would see that the blue wave is down below quite a bit and the red wave is up above the midline a little bit. So we would subtract those heights to get a common position kind of where that pink dot is. For the point marked B, both of the waves are at the same point, and so they would combine together and create a bigger wave below the midline. At point C, similarly, the blue and the red wave are at the same position at that moment, and so they would combine together, they would double in height. At position D, again, same sort of a thing. And then at position E, we would see how there's a bigger amount down below the midline, a smaller amount above, and so the net result of those two waveforms would be somewhere around here. You could continue looking at some other spots along the way, and what you're basically going to get is sort of a resultant wave that's pretty much a mess for most situations. But there are some very particular frequencies where something unusual happens. Take a look at this particular frequency and notice how the wave really builds upon each other. We get bigger and bigger swings even though the wave itself doesn't seem to be moving. We call this a standing wave. It happens with other frequencies as well. So this particular frequency for the incident wave produces sort of 1.5 waves on the string. This one produces 2 full waves that sort of oscillate up and down. It seems to stand in one spot. And then there's one frequency that is actually the easiest to be created because it really is just an oscillation up and down. And this actually is being created by a wave that is continuously being pushed to the right, and then it reflects and comes back. And as those two waves interfere with each other, this particular shape is created. This frequency is called the fundamental frequency. It produces the sort of the smallest amount of a wave that fits between the endpoints. This is what defines a fundamental frequency, and it's the frequency that corresponds to a particular pitch that we're going to hear from an instrument, sort of what its natural frequency is. So the terms fundamental and natural tend to be used the same. For those of you with a little bit of musical background, this is actually what's called the second harmonic. It would represent an octave above the fundamental. This would be the third harmonic and the fourth. Most of us don't need to know this, but again, if you have a little bit of musical background, you might have heard those terms. This refers to when you play a note on an instrument, you mainly hear the fundamental frequency, but you will also hear above it some second, third, and fourth harmonics that add the special qualities, the special tones of that particular instrument. Okay, so in a standing wave, a wave where you are, where it is oscillating at just the right frequency, there are certain points on the wave that do not appear to move. Okay, these are spots where the waves always completely cancel each other out. There's destructive interference at these particular points, no matter where you are within the wave's motion. These are called nodes. Then there are other points where there is the greatest fluctuation of the wave. These are called antinodes. Let's stop this and take a look at some waves in general. So very often when we draw these standing waves, we show a couple of snapshots so that we can see not only this moment in the wave, but also this moment. And it just helps us see the whole wave. But the darker line would represent one particular moment. I'm going to use N to stand for a node and A to stand for an antinode. So our nodes are places where there is no motion in the wave. An antinode represents a spot where there is the most motion, the greatest displacement, and they're evenly spaced in between all of the nodes. Now, stringed instruments really connect very well to what we've just seen here, because when you pluck a stringed instrument, you are creating these sorts of standing waves on the string. The fundamental is the one that comes out strongest, and that's the main note that you'll hear. But you will hear some other notes on top of it, which make it sound nice. It's what makes a violin sound different from a guitar. The way the harmonics are built on top of the fundamental frequency. When the string is plucked, or maybe strummed, or even bowed, you will again naturally hear that main frequency, that natural frequency or fundamental frequency. This is corresponding to the lowest energy level. It's the easiest thing to be created. And so it's generally going to be the strongest note that you hear. If we know the length of the string and the speed of the wave along that string, we can actually predict what frequency we would hear when we pluck or strum that string. And we just need to use our ideas of V equals F times lambda. And again, we would need to know the speed. It's usually going to be given to us, although in case you're interested, there is a connection to how tight the string is, the tension in the string, and also what's something called mu, which is the mass density of the string. It's how thick the string is. Let's take a look at an example of what I mean by this. So imagine that we have a particular guitar string where for whatever reason we know the speed of the waves based on the tension and the type of string being used. Let's determine what the fundamental frequency is, what the main note will be if the string has a length of 76.5 centimeters. So first of all, we want to picture that fundamental waveform. Okay, this is what we mean by the string being 76.5 centimeters long. It means that the ends of the string are attached at those points, and when we pluck it, we would mainly produce this wave. We want to see that this waveform is half of a wave. And so the relationship between the length of the string, which I'm calling L here, is that the length is 1/2 of a whole wave. So we could plug in our 0.765 after I've converted that to meters, and we would find that our wavelength is 1.53 meters. Then we can turn to the wave equation, and we are looking for the frequency. So we would end up taking the speed we were given divided by this wavelength, and that would determine the note that we hear. So this corresponds to a particular note or pitch that we would hear on this guitar string. Now, if instead we have a wind instrument, which is an instrument that you are going to blow into or blow across, there's a slightly different pattern that's involved. There's a different reason why waves are being created, because obviously we're not plucking a string. The idea here is that when you blow into or blow across these sorts of instruments, there are waves that are created in the air inside the instrument. And so it is the air that is carrying the wave. The air is the medium for the wave. Some wind instruments have two ends that are open, like a flute or a recorder. And these are referred to as open pipes because both sides of the instrument are open to the air. What happens here is that the air pressure, our normal air pressure, keeps the air pressure of the ends of this pipe at a very consistent level. So they are nodes of pressure. The word node meaning something that remains consistent. But the particles near the end up moving quite a bit because of those, the pressure that's on there. They are antinodes. This kind of represents that idea. So the particles are moving a lot at the ends where someone is blowing across or at the end of the pipe, but the pressure remains consistent. Either way, though, we want to notice that the middle is the opposite. So if we're looking at pressure, the pressure in the middle is going to vary quite a bit. If we're looking at the particles in this picture down below, you can kind of see how the particles in the center don't really move very much at all. It's the other particles further on the sides that are moving quite a bit. The important thing here, though, to understand or to sort of notice is that there is a half of a wave that is fitting within this pipe. And that's what we're going to use to determine what frequency that pipe would produce. That's the key idea if you're writing something down, that half of a wave fits inside an open pipe. A closed pipe is one where one end of it is closed, the other side does have to be open, otherwise it's not a pipe at all. And most wind instruments are actually closed pipes. Most of the time, somebody puts their mouth over the end of it and blows into it, blows across a reed, something like that, but the end of the pipe is closed. In this case, the pressure is going to be still held constant at the open end, but the place where the person is blowing actually is going to have wide changes in pressure. So at the closed end, there are lots of changes. It's an antinode of pressure. And the reverse is happening for the particles. The particles do not move tremendously near the closed end, but near the open end, they move quite a bit. So hopefully as you look at this one's a little harder to see, but this actually corresponds to a quarter of a wave. And so the key relationship, the key pattern we want to see here is that 1/4 of a wave fits inside of a closed pipe. Let's take a look at a couple examples. A mini project that will be offered is to build a pan flute out of straws. When you blow across the straw is going to be an open pipe. Let's assume the air temperature is a pretty normal 15 degrees Celsius and that we are trying to produce a frequency of 600 hertz. We can figure out how long the straw will be by again considering what that open pipe pattern would be. It would be a half of a wave that we would need to figure out. We need to know what the wavelength is of this in order to figure out what the length of the pipe should be. So let's start with the ideas of the temperature. So the medium for the waves is going to be air. That's what's inside the pipe. So we need to know the speed of sound in air. Recall that if we take 331 plus 0.6 times the temperature, we can determine the speed of sound, the speed of our wave inside the pipe. We can then use this to determine what the wavelength should be, taking 340 meters per second and dividing by the 600 hertz that we're trying to design this instrument to be. That gives us our wavelength. And then looking at our diagram, again, we see half of a wave here. So the length should correspond to 1/2 of a full wave. Plugging in our known value, again, notice here we knew the wavelength. We're trying to find the length. That tells us to use a straw that's about 28 centimeters long. Here's another example, but this one involves a closed pipe, because what's important here is the air column that is up above the bottle, okay? And the one end of it is closed off by the soda. The other side is where we are blowing across. You've probably done this before. You blow across a soda bottle and you hear this kind of low noise, this certain sound that is created. Let's figure out what pitch or what frequency our instrument is playing. So again, it's a good idea to imagine the shape of the wave that is fitting within this pipe. It would be turned a quarter turn here, but the idea is that there would be a pressure node at the top and a pressure antinode at the bottom. And so 1/4 of a wave would fit inside. We need to know the length of this air. To do that, instead of just using 22 or 14, we would have to subtract those two values and see that the air column up here is 8 centimeters long. That is going to be the length of our closed pipe for this example. Since our waveform is 1/4 of a wave, we could write a statement like this, that the length of the pipe is 1/4 of the full wave. Plugging in the value we know for the length, we can see that the wavelength would end up being 0.32 meters. And then as the problem said, we're going to use the same temperature from the previous problem, meaning the same speed, which was 340 meters per second. So using our wave equation, we can determine that the frequency is pretty high in this case, 1062 hertz. Now let's say you drank some of the soda, and so the height would change a little bit. Let's imagine that it drops down to just 6 centimeters of soda in the bottom of the bottle. Let's figure out what our instrument plays now. So what would change is this value of the length, because again, we need to know the amount of air that is vibrating, not the amount of liquid. So 22 minus 14 gave us 8 in the previous problem. But here we would take 22 minus 6 and get 16 centimeters or 0.16 meters as the length of the column of air. Notice that that's double of what we had before. Keep that in the back of your mind here. So we would instead use 0.16 as our length, and we would instead get 0.64 as the wavelength. Again, notice this is doubled as well. When we plug this into our wave equation formula, we get 531 hertz. Looking again, before we had 1062, now it's only 531. So the frequency was cut in half. And in fact, this is an octave lower if you actually perform this experiment.